All right, today's lesson is on graphing radical functions. We're going to focus on square root functions. So today, the objectives are to create a table of values given a radical function. Okay, and that's going to require us to understand what values of x to pick. All right, then 2 is graph the radical functions, transform, so shifting. Okay, so we're going to be looking at h and k and a today, and then be able to state the domain and range of radical functions. All right, so the first slide, it says complete the table given f of x and the x values, then sketch the graph. All right, so they want us to find, okay, the y values of square root of x when x is -3, -2, -1, and so on. So all you have to do is plug those in, okay, and then type it in. So when you plug in -3, it's the square root of -3, which is imaginary. So we're just going to write, so on a graph, on a real coordinate plane, okay, that is DNE, does not exist. All right, so that's going to be true for all of the negatives. What that means, okay, is that this graph does not exist when x is negative. Right? So that means the domain does not exist when x is negative. So the domain is going to start at 0 and then be all positive numbers. Okay, so when we plug in 0, the square root of 0 is 0. Square root of 1 is 1. Okay, the square root of 2 is rad 2, right, which this automatically converts to a decimal, 1.414, it's irrational. We have rad 3, and then rad 4, which is just 2. All right, so here's our table of values. So if we want to plot this, let's see what this might look like. All right, so 0, 0, we're going to have a point right there. 1, 1, point right there. Okay, at 2, it's 1.4. At 3, it's 1.7. And at 4, it's 2. All right, so our graph, this little curved graph here, is going to go up at that rate. All right, and so just thinking about some of those objectives, right, making a table of values from the easiest x's. So what are the easiest x's? They're the ones that exist. So you never want to plug in an x that makes the inside of the radical negative. All right, and we're going to talk about shifting this with h and k's, and then we'll even find a better way, okay, to know where to start, because that's going to help us identify the domain and range. All right, so now based on the graph, can we type the function? All right, so we have this 0, 0, okay, at 1 it's 1, at 4 it's 2, right, at 9 it's 3, so this is just the function that we just graphed. So it's just the square root of x. Okay, so square root feature right there, x, and there now you can see matched up. All right, just looking at this graph, what do we notice about this graph, right? We notice, right, it starts at 0, 0. We're gonna call that a critical point. It's an initial point. Some people call it the starting point, initial point. It's critical point because what if the graph is going the other direction? Then it's the end point. All right, so it's either the initial point or the end point. Okay, we'll just call it the critical point for now, kind of like the vertex was a critical point of a parabola. This starting point is the critical point, okay, for the radical function. And what do we notice? We notice the graph does not exist below the x-axis. So the range is everything above the x-axis. So the range would be y is greater than or equal to 0. And same with the domain here. The domain starts at 0 and continues on everything to the right. So our domain would be all real numbers greater than or equal to 0. All right? But we're going to talk again later on about shifting this over and down, and so maybe even reflecting it. So we'll see other domains and ranges. All right, so I kind of jumped ahead of myself here, and that's what this slide is. What do we notice, right? We notice that the x's are always greater than 0, so domain, right? We notice x is greater than or equal to 0. I use the math symbol here, greater than or equal to 0. All right, we notice that the range is y is greater than or equal to 0. All right, so that's what we noticed at that graph. Okay, what are we still wondering about? Is it always going to be that? Does the domain and range change? Okay, I'm curious about that. And if so, what makes it change? All right, and so here we have a radical function. Okay, this is the I guess you could call it the standard form of a radical function, of a square root function. It has all the pieces into it. Some people might call it the transformation form because we're shifting it. The other one was called the parent function, was just square root of x. So notice these three letters. We've seen these before, a, h, and k. Right? We've seen them in absolute value functions. We've seen them in quadratic functions. All right, so we know what these do. All right, what do? They shift our graph up and down. That's the k, right? The h shifts it left and right, and the a is going to stretch or compress. And if the a is negative, it reflects it over the x-axis. So let's just take a look at those. So let's start with k. Right. If I make k bigger, you can notice how the graph goes up. Right now, I make k 5. Okay, look at that initial point. What's the initial point now? Now it's 0, 5. It moved the initial point up 5 spots. Okay, so if I move it back down to 0, okay, what do you notice about the initial point? Right now it's 0, 0. Hasn't been shifted yet. What if I make k negative? Okay, well, now it goes down. Okay, so now k is negative 3, so the initial point is 0, negative 3. So now my range would be different here. Now my range would start at negative 3, be all real numbers greater than or equal to negative 3. All right, let's put that back at 0, and let's mess with h. Okay, h is the horizontal shift, right? So as I make h positive, it moves it to the right. So if I make h 5, it's been shifted 5 spots to the right. But remember, right, when you plug in that 5 in the formula, it looks like x minus 5. Remember, the h is always the opposite of what you see there because it's written x minus h, the opposite of h. Okay, so, right, and if I make h negative, it's going to move it to the left. Right, so h is going to move things left and right. It's moving that critical point, and the rest of the graph obviously follows. Right, now what about the a? So the bigger I make a, the faster it should grow. It stretches it out. The smaller, the closer I make a to 0, right, the slower it grows. It compresses. Now, what if I make a negative? Now all the y values become negative, right? So it flips. Now the range would be all real numbers less than or equal to 0. All right, so we have to pay attention. The a is going to affect the direction, okay, that the graph is going, which the direction then affects the range, right? And it affects how fast it's changing, how fast the graph is rising. All right, so same thing that we've always done here. All right, a stretches, compresses, reflects. H is the horizontal shift, and k is the vertical shift. And just like h and k control the vertex of a quadratic in vertex form, h and k control the initial point. All right, so now we just want to practice typing a radical function in. Okay, you could type it or you could handwrite it. Okay, so we want to plug in all of these values here. So we have f of x equals, and here a is 1, so I don't need to type that. I mean, I can. I'm just going to show you everything, but then I'll show you the best way to do it. Okay, and then the square root symbol. x minus h, so h is 2, so x minus 2, and k is 0, so plus 0. All right, so that's technically correct, but we know that we don't need to write 1 when we're multiplying by 1, so we don't need that 1. Okay, and we also don't need to add 0, so we should just write this as f of x equals x minus 2. Right, so just thinking based off of what we just learned, right, the critical point, right, would be hk, right? I'm shifting this graph 2 spots to the right. So on the parent function, the critical point was 0, 0. So 2 spots to the right means that my critical point is going to be 2, 0. All right, so let's look at the graph. So let's type in, okay, that exact same function that we just had. So f of x equals the square root of x minus 2. Let's see if what I was talking about was correct. And it was, right? The initial point is 2, 0. It shifted it 2 spots to the right. All right, notice it's still going up, okay, and to the right. What would make it go down would be if a was negative, right? If I just made a -1, the graph would be going down. All right, notice that, right, it doesn't go down. Let me see if I can, right? Because if it did, right, it wouldn't be a function. Okay, so it wouldn't pass the vertical line test. All right, so we don't graph the plus or minus of the radical. We only graph the principal outputs of the radical. All right. Okay, so what was the critical point? So again, it was 2, 0, 2, comma 0. Again, we know, okay, the critical point is always h comma k. All right, so in this case, h is 2 and k is 0. So even without looking at the graph, we should be able to understand what the critical point is. And knowing the critical point is going to help us graph when we're only given the function and not the graph to start with. All right, what is the domain and range? All right, so maybe we need to look back at the graph at this one. Okay, so let's do that for our beginner's sake here. So where is the lowest x value? Remember, the domain is the x values. What's the smallest x value? The smallest x value is 2. Then it continues on forever. Remember, if it hits the window frame, it means it continues on forever. So it's going to go right forever. So the domain is going to be from 2 to infinity. Are all real numbers greater than or equal to 2? The range is the y values. What's the smallest y value? The smallest y value is 0, right? And now the graph goes up forever. So the range will be all real numbers greater than or equal to 0, or in interval notation, 0 to infinity. All right, so let's jump back. Okay, so let's go ahead and I guess we could type in both. Okay, we'll do interval notation. Okay, 2 comma infinity. And that's going to get the parenthesis. Okay, or if we do it in inequality notation, it's going to be x is greater than or equal to 0. Okay, you could use either notation. Okay, the range was all real numbers greater than or equal to 0. So that's going to be 0 to infinity. An interval notation, or y is greater than or equal to 0. Sorry, on the domain, my bad. Let me fix that. I don't know why I wrote 0 there. That's 2. All real numbers greater than or equal to 2. Okay, so sure you understand I typed in the wrong number there. I did interval notation correctly, 2 to infinity. I just typed in the inequality notation wrong. X is greater than or equal to 2, the starting point. Sorry about that. All right, so where is the critical point of the given radical function? So here we have no graph. We're just given a function. All right, so we want to identify our h and k. Right, so this graph right here, there's no a, which doesn't affect the critical point anyways. right? So A is 1. The H is -1. This is shifted one spot to the left, and then K is -2, two spots down. All right, so one spot to the left, if you're starting at -1, is -1, and then two spots down will be -2. My critical point is -1, -2. Again, that's just H comma K. And H is -1, K is -2. Where's the critical point for this given radical function? So again, A is -2, that doesn't affect the critical point. All right, so H is 5 and K is 1. So it's just 5 comma 1. Again, remember H is the opposite of what you see there because the formula was X minus H, the opposite of. All right, so it's not -5, it's +5, 1. To the right, 5 spots, up 1 spot. All right, here's the graph of that function. So let's just check our initial point. Was that correct, right? 5, 1, it was. All right, now look at this graph. It's going down forever. Why? It's been reflected because A is negative. Okay, so notice that -2, that's going to reflect it. Okay, and it's growing faster, right? I went, right, a lot faster here than the other one. So it's being stretched. Okay, you can see, remember this is counting by halves here. So down 2 over 1, down 2 over 1. Okay, so that makes some sense there. All right. Okay, how did the A of -2 affect the graph? So again, it stretched it and it reflected it. It stretched the graph by a scale factor of 2 and reflected the graph. All right. What's the domain? All right, so the domain, remember the initial point, okay? The initial point was 5, 1, and it went to the right. It's everything greater than 5. So in interval notation, 5 comma infinity. Okay, remember, infinity always gets the parenthesis. If I'm doing inequality notation, right, it's going to be x is greater than or equal to 5. Right? The range now, okay? So the initial point was the highest point on the graph. So the highest point was 1, and then it went down forever. So the range in interval notation is going to be -infinity, comma 1. Or y is less than or equal to 1. Right? So let me jump back to that graph so you see that. Okay, the highest point is 1, and everything is below it. So the range is all real numbers less than or equal to 1. And that's how I got my answer there for the range. All right, so now we want to type this function in here. Okay, so we got the radical function. Okay, what is it? So, well, I should be easily able to identify my h and k. My h is -1, and my k is -3. All right, so let's start there. So we don't know a yet. Okay, well, let's start with h and k. So it's going to be x plus 1. And notice how it shifted it to the left 1 spot. Yeah, that's not right. So now I've got to shift it down 3 spots, so -3. All right, so it matched up, so that means a is 1. Okay, up 1 over 1, up 1 over 3, up 1 over 5. Okay, so again, let me show you that one more time. Up 1 over 1, up 1 over 3, up 1 over 5. 135. All right, now what about this one here? All right, so now I've shifted 2 spots to the right and up 4. So same thing, let's start with the square root. We're going to start with the assumption that a is 1. If we have to change it, we'll change it at the end. Okay, so x minus 2. So you can see that it shifted it over 2 spots to the right, and now up 4 plus 4. And we got it. All right, so just by matching that initial point, okay, we see that we can match the graph to the equation of the function. All right, but in both cases, a is 1. What happens if it's stretched or compressed or reflected? We are going to have to try to find a out, and we'll talk about how to do that. But again, from the initial point, up 1 over 1, up 1 over 3, up 1 over 5. Okay, so maybe there's something brewing there. All right, so this one is definitely not going to have an A or 1. Look at the starting point's the same. So if I type in that same thing that we just had, x minus 2 plus 4, I'm going to get the right initial point, okay, but I definitely don't have the right graph here, right? It's not being stretched enough. It's being stretched. It needs to be bigger, all right? So maybe, let's see. When I went over 1, how far did I go up? I went up 2. So I'm thinking maybe A is 2. Okay, I've seen this before, right? From the vertex, from the critical point, okay? Now we don't call this a vertex with radicals, but in a parabola we do. Right? This is the initial point, the critical point. From that critical point, right? What was that rate? If I go over 1, what's that rate up? Okay, that rate's 2. So maybe that's my A. So let's try 2. And we're right. So maybe we got something brewing there. 1 over how far up? That might be always A. All right, and again, another one, okay, with 2, 4. All right, so again, if I type in the square root, x minus 2 plus 4, okay, but now it's going the wrong way. All right, so now, okay, it's negative, but when I go over 1, how far did I go down? I went down a half. Okay, notice that, right? Over 1, down a half. Over 1, down a half. Again, remember, okay, that these are counting by halves, right? So it's 2.5, 3, 3.5, 4. So over 1 whole, down a half. So I'm going to think A is negative 1/2. And it is. Okay, so how can we figure out the A value? All right, so when you go over 1 from the critical point, right, then count how far up or down, and that is your A. Let me go back, explain that one more time. Okay, from the critical point, you go over 1 and you count how far up or down, and that's your A. I'm counting down in this case, down 1/2. So A is negative 1/2. On the previous one before that, okay, from your critical point, you go over 1, count up 1, 2. I went up 2, so A is 2. All right, and then just a side note, there is an algebraic way, okay, to figure this out. All right, and so you could always plug in, okay, your H and K, which you know, and then pick any point on the graph and plug in X and Y, and then just solve for A. All right, so for example, if I come back to this one, okay, and um, Okay, so to show you algebraically, all right, so say we know that it's y equals, we don't know a, right, square root of x minus 2 plus 4, right? So if I could pick, okay, another point, not the critical point, okay, but if I pick this point right here, which is the point 6, comma 3, right, and I plug that into x and y. So y is 3, so I go 3 equals a square root of 6 minus 2 plus 4. That's a plus sign. Okay, I should be able to solve this for a. So I subtract 4 from both sides. I get negative 1 equals a times the square root of 4. And the square root of 4 is just 2. So I get negative 1 equals 2a. Divide by a, so a equals negative 1/2. So we can algebraically figure out a, or we could use that pattern over 1 up and down how many. All right. All right. Moving on. Okay. So if a is 1, what is the rate of change, okay, pattern from the critical point? So this is what I was trying, okay, to show you there. And so did we recognize something? Have we seen this before? Remember, quadratics and radicals are inverses of each other. So on a quadratic, it was, over 1, up 1, over 1, up 3, right? Or if you want to say it the other way, up 1 over 1, up 3 over 1, up 5 over 1, okay? Now with a radical, it flips it, okay? And so it's up, right, and over, but it's flipped. So again, on the quadratic, right, we were over 1, up 1, over 1, up 3. It's going to change that, okay? Now we're running further and up and over. So we know that the pattern is 1, 3, 5. All right, but it's over 1, over 3, over 5. All right, and so that's what we're looking for here. It's up 1 over 1, up 1 over 3, up 1 over 5, and so on. If a is 1, those overs are going to or the ups will change if the a changes. So it could be up 2 over 1, up 2 over 3, up 2 over 5. All right, so if the a's change. All right, so you can see it here. There's a better way for me to explain it, right? On the parabola, on the red graph here, right? It's over 1, up 1, over 1, up 3, over 1, up 5. Or again, if you want to do rise first, up 1 over 1, up 3 over 1, up 5 over 1, right? And on the radical, okay, it's up 1 over 1, up 1 over 3, up 1 over 5. All right, and so that's the pattern. Okay, if we make a 2, okay, what's going to happen now? It's up 2 over 1, up 2 over 3, up 2 over 5. So the over didn't change. The a, okay, is again affecting the output, so it's affecting the rise, the y values. All right. Sketch the graph. Okay, so we're going to make a table of values. What should be the first point in my table of values? It's going to be my critical point, right? Where does the graph even start from? So it starts at 6, 2. So my graph is 6, 2. Okay, so now I could pick any x's bigger than 6, because remember, the inside has to be positive. Okay, so if I plug in 7, 7 minus 1 is 1, square root of 1 is 1, 1 minus 2 is negative 1. Okay, sorry, my critical point is 6, negative 2, right? So, and then 7, negative 1. Now, if I plug in 8, okay, which I could do. I get 8 minus 6, which is 2. Square root of 2 is irrational. That doesn't help me. All right. So what I want to do is I want to find out what's going to make that a perfect square. So if I just use the pattern, right? So this was over 1, then it's over 3, then it's over 5. So over 3 from that's 10. So if I plug in 10, 10 minus 6 is 4. Now I got a perfect square. Square root of 4 is 2. 2 minus 2 is 0. Okay. Then over 5. Remember 1, 3, 5. So this will be 15. Right? And this will be positive 1. And then we could check 15 minus 6 is 9. Square root of 9 is 3. 3 minus 2 is 1. If I wanted to keep going, there's no point because I'm out of room on the graph, but it'd be 22, 2. Now it's over 7. Over 9 would be 31, 3. Right? So if I wanted to graph this, all right, so 6, negative 2. Oops, I didn't go down far enough. Undo. 6, negative 2. 7, 1. 10, 0. That's all that's going to fit on my graph. That's what my sketch would look like. Right 6, down 2, boom. And again, without a table of values, I'd go up 1 over 1, up 1 over 3, up 1 over 5. Okay, so how do you pick your x values, right? So you start at the initial point, that's h. Then add 1, then add 3, then add 5, and so on. It's always going to give you that perfect square inside the radical. All right, what was the domain of that previous one? So again, where did it start at? It started at 6 and then goes on forever. So my domain is going to be 6 comma infinity. And then the range, okay, starts at negative 2 and goes up forever. So negative 2 comma infinity. All right, sketch the graph and create a table of values. All right, so I'm going to do this a little bit backwards. I'm going to sketch the graph first, and then I'll come back and make the table of values. But just to show you that I don't need, okay, the table of values necessarily. So I know where I'm going to start, HK. Right, so HK is 1 or negative 1, negative 4. Now my A is 3. So now it's up 3 over 1. Up 3 over 3. Up 3 over 5. All right, so just using the pattern, that's going to be my graph right there. All right, so let's check to see if we're right. So again, starting with the critical point, negative 1, negative 4. All right, and then what do I need to do? Again, I need to add 1 to that, so that's 0. I'm going to add 3 to that, that's 3. I'm going to add 5 to that, that's 8. Okay, so if I plugged in 0, 0 plus 1 is 1, square root of 1 is 1. 1 times 3 is 3. 3 minus 4 is negative 1. So did I get 0, negative 1 on my graph? I did. Plug in 3. 3 plus 1 is 4. Square root of 4 is 2. 2 times 3 is 6. 6 minus 4 is 2. So I should have the point 3, 2 on my graph. And do I? I do. All right, plug in 8. 8 plus 1 is 9. Square root of 9 is 3. 3 times 3 is 9. 9 minus 4 is 5. All right, do I have 9, 5 on my graph? Okay. Or sorry, 8, 5 on my graph? Yes, I do. 8, 5. All right, so I could do it without the table by using the pattern, right? The pattern will be up A over 1, up A over 3, up A over 5, right, from the initial point. So we could just always use that pattern when graphing, again, or it could be down if A is negative, it could be down, right? So, or we plug in numbers in the table of values, and to pick the right x's, we're still using that pattern to help us pick the x's, right? Over 1, over 3, over 5. So either way, that pattern is critical. If we don't follow that pattern, we're going to get irrational numbers over here, which is okay, but it's just not that easy to graph them. So it's easier when you get all these integer values here. Domain and range, okay, so the domain starts at -1, so it's -1 to infinity. Oops, wrong symbol. -1, comma, infinity. And then the range starts at -4 and goes up forever. So -4, same thing. -4, comma, infinity. And there you go. So again, the domain and the range is really tied into that critical point. The domain's going to start at H, right? Or end at H, and then the range, same thing, is going to start or end at K. All right, so if we want to match, we want to try to match these graphs up. So which graph is going to match, okay, with x plus square root of x? That's shifted 3 spots to the left. So that looks like that one. All right. And then which one's the parent function? So that looks like this one. This one shifted 3 spots to the left, but has an a of 2. So it's up 2 over 1, up 2 over 3. So that's that one. And then this one is shifted left 3, down 4. So it must be that last one there. Oops. Okay. So we got those all matched up. And then the last slide is just if you guys have any questions for us while we're doing this in class for you to do that. All right. All done. Thank you.